For decades, we've basically taught computers to see with a magnifying glass. They could spot tiny little clues, but they often missed the big picture. Well, today, we're diving into a completely different approach, one that teaches them to see the entire scene all at once. And it all kicked off with one simple question.
Right, this question gets to the absolute heart of a massive challenge in AI. For so long, our best models were amazing at identifying the individual trees, a car, a person, a cat, but they were kind of blind to the forest, how all those things actually fit together. And cracking that problem, well, that led to the breakthrough we're talking about today. So, to really get why this new way is such a big deal, we first need to talk about the long-reigning champion of computer vision, the convolutional neural network, or as you probably know it, the CNN. For years, CNNs were the absolute kings. The best way to think about them is that they use this little magnifying glass to scan over an image. They slide these tiny filters across the picture, one small piece at a time, looking for really specific patterns. An edge right here, a curve over there, maybe a bit of furry texture. Now, this whole approach is built on a few really clever shortcuts. First is locality. It just assumes that to understand a single pixel, you only really need to look at its immediate neighbors. Then there's translation invariance, which just means a cat is a cat whether it's in the top left or the bottom right. And finally, weight sharing, which lets the model reuse its cat ear detector all over the image. Super efficient, right? But these assumptions also create a huge blind spot.
Because this is exactly where those clever shortcuts start to break down. What happens when the most important clue isn't what's right next to something, but what's happening on the complete other side of the image?
And this example just nails the problem perfectly. Because a CNN only really cares about those little local patterns, its car detector goes off just as loud whether that car is on a road or parked on top of a skyscraper. It completely lacks the global context to say, hey, wait a minute, that doesn't make any sense. It sees all the parts, but it totally misses the story.
The solution, and this is the really cool part, came from a totally different field in AI, the world of understanding human language. This was the title. A groundbreaking paper from Google back in 2017 that introduced what we now call the transformer architecture. It was built for stuff like language translation, but, well, it ended up changing pretty much everything in AI.
Just look at this timeline. It shows you how fast the whole landscape flipped. In 2015, these advanced CNNs like ResNet were the undisputed champs of computer vision. But just 5 years later, by 2020, the core idea from a language model was suddenly beating them at their own game. So what was this magic ingredient?
It's a mechanism called self-attention. Here's how to think about it. When you read a sentence like, "The cat sat on the mat, it was fluffy," your brain instantly knows that it refers to the cat, not the mat, right? Well, self-attention gives an AI that exact same superpower, the ability to look at every single word in a sentence and figure out how it relates to every other word all at once. It's the key to understanding context.
And this led a few researchers to ask a truly brilliant question. What if we could get a computer to read an image the same way a transformer reads a sentence?
And the process is actually surprisingly simple. First, they just chop the image up into a grid of little square patches, kind of like turning a photo into a mosaic. Then, each of those patches gets squashed down and treated like a single word. They string all of these image words together into a long sequence, add a little note about where each patch originally came from, and then they just feed that entire sentence of patches into a standard transformer.
This changes everything. See, a CNN is basically born with this built-in assumption that nearby pixels are the most important ones. A vision transformer, or VITE, has no biases at all. It's a blank slate. It looks at all the image patches at the same time and uses that attention mechanism to figure out for itself which patches are important to which other patches, no matter how far apart they are. It literally learns the entire context from scratch.
But, and you knew there was a but coming, right? This incredible new flexibility, this power to learn everything from the ground up without any assumptions, well, it comes with a pretty significant price tag. So is this new global way of seeing always better? The answer is a hard no, unless you can feed this thing an absolutely colossal amount of data. This chart tells the whole story. On the left, you can see that when you train both models on a standard dataset with about 1 million images, the classic CNN actually performs better. But now look at the right. When you pre-train them on a massive, private dataset with over 300 million images, the vision transformer doesn't just catch up, it blows right past the CNN. 300 million.
Just let that never sink in. That's how many images it took for the vision transformer to learn the basic rules of vision that are just hard-coded into a CNN from day one and then eventually surpass it.
And this quote just nails it. Because the VIT doesn't have that built-in common sense of a CNN, it needs to see a truly astronomical number of examples just to figure out basic stuff like textures and shapes on its own. It has to learn everything, and that takes a mind-boggling amount of data.
So, okay, let's zoom out. What does this all really mean for the future of AI? What's the big takeaway from all this?
What we're really seeing is a fundamental change in philosophy. For years, making progress in AI was all about designing these highly specialized, handcrafted tools for each job, a special architecture for vision, another one for language. The vision transformer points to a totally new direction. Just build one general-purpose learning machine, feed it an insane amount of data, and let it figure out the rest for itself.
And this leaves us with one final and pretty challenging thought. If the state-of-the-art now depends on having access to these massive, private datasets and the incredible computing power needed to crunch them, what does that mean for innovation? It raises some really big questions about access, about resources, and ultimately about who gets to build the future of artificial intelligence.